Okay, in video 1 we learned that a vector is a quantity that has magnitude and direction, that it can be named either by its components, which are multiples of an x vector in the x direction called vector I, and a vector in the y direction called vector j. For example, negative 7i plus 5j is a way to name a vector. It can also be named by its magnitude and direction. So if we look at the second example, we can name vector b as a vector that is 9 units long at an angle of 280 degrees. Now what we're going to do in this first part of our example is to use these formulas to convert from one way of naming a vector to another, and also show how they are shown on a grid. One way, remember we talked about a vector can be moved anywhere in any position as long as it's pointing the same direction, it's the same length. But it's very convenient to name a vector using a grid and put its tail on the origin and its tip somewhere on this grid. Now, using components is especially useful for using the grid method. So negative 7i plus 5j means that its x component has a length of negative 7 and its y component has a length of 5. Both of these are vectors, so I'm going to draw them. Negative 7 would be a vector going in the negative y direction, and then positive 5. 1, 2, 3, 4, 5. So my vector, and I'm going to use a different color, so vector A is this vector right here that goes, we have negative 7 here, plus 5, and this would be vector A. Now, could I name the magnitude and the direction of this vector? So in other words, how long A is, and what is this angle right here? So using our formulas, let's do that. Basically, this is right triangle trigonometry, so it's not hard to remember these formulas if you know your triangle trigonometry. So I know that this side is 5, and this side is negative 7, and so I can say that the magnitude of vector A is the square root of negative 7 squared plus 5 squared, which is the square root of 74, or approximately 8.6 units. Now, to find the angle, we're going to use inverse tangent. Inverse tangent of y over x, which is 5 over negative 7. Now, you might think, well, didn't I just find this angle? Well, no, I won't find this angle because if both of these were positive, yes, I'd be finding that angle, but one's positive and one's negative, so I'm actually going to be finding an angle that's in quadrant 4. So if I do this on my calculator, inverse tangent of 5 divided by negative 7, I get negative 35.5 degrees. Negative 35.5 degrees. Now, where is that? That's actually down here. So how do I find the angle I want? Well, the difference between these two angles is going to be 180 degrees. So I just need to add 180, and what I end up getting then is the true angle, which is, let me add 180 to this, okay, 144.46 or 144.5. And that looks really reasonable. If I look at this angle, that looks really reasonable. Now I'm going to erase this down here now because I'm going to be needing that space for the next vector. Now my next vector is 9 units long and the angle at an angle of 280. Now this is going to be a little trickier because when you draw it at an angle, it's going to be hard to measure the 9. I'm just going to have to estimate that, and I'm also kind of having to estimate my angle. I know that going around, all the way around from 0, my mouse is not behaving, from 0 all the way to here is 270, so I need to go a little past 270 and try to make this about 9 units long. So I'm going to do this to the best of my ability. I'm going to say that it's about there. That's probably a little bit too long, slightly too long. Now I'll be able to correct this later when I put in my components, and I may redraw this, but that's basically what it looks like, all the way around to 280, about 9 units long. Now, if I go up here and look at my components, it says that my x component is just the magnitude of the angle, magnitude of the vector times the cosine of the angle, and my y component is the magnitude of the vector times the sine of the angle. So x is equal to 9 cosine 280, and y is equal to 9 sine of 280. And I'll get the lengths of the two vectors. And because cosine of 280 is this is quadrant 4, is going to be a positive number, sine of 280 in quadrant 4, that's going to be a negative number. That gives me a positive x and a negative y component, which is what I would expect to get. So let me do those both on the calculator. Okay, you can see I did those in the calculator, and I got positive 1.56 and negative 8.86. Usually I like to go to about 3 decimal places, so I'm going to call that 562 and 863. So negative or positive 1.562 and negative 8.863. I'm going to double check. Now this will allow me to more closely plot this vector. So I'm going to erase my vector and redraw it using the components now. 1.56, that's about right here, negative 8.8, about right here. So it looks like I was pretty close when I drew the vector before, but this is a little more accurate here. Okay, now that I'm done drawing my two vectors, how do we go about adding two vectors? How do we add two vectors? So I am once again going to erase some of the other information I have on here so that we can more clearly see what I want to see, which is how to add two vectors. Now think about if these two vectors, and I'm going to put my vector b on here, and I'm also going to group these two together so I make sure that I get everything I want. I don't want that little piece. I think I'm going to erase just a little bit more and group this together so that when I move it, it will move as a unit. And make sure that's all together. All right. Now, when I add two vectors, think about if this were a force pulling two different directions. If something was pulling on the same object, this direction and this direction, what way would you expect to see the object move? Well, clearly it's going to move kind of in between here. It turns out that when you add two vectors, they have a really specific geometrical relationship. So we're going to start by using one way of adding two vectors, and that's by adding their components. And I didn't actually finish writing this using components. Vector b could be written as 1.562i minus, and with a little vector hat over it, minus, I put the vector hat in the negative sign instead, minus 8.863j. Alternately, it could be written as 1.562 comma negative 8.863. So that's another way. And basically, notice those are just the coordinates of the tip of the vector when its tail is at the origin. Now, if I want to add two vectors, the easiest way to add the two vectors is to add their components. So I can say vector A is negative 7i plus 5j. Vector B is 1.562i minus 8.863j. Now to add those, I just add their x components and I add their y components, and the resulting sum are the components of the vector sum. So negative 7 plus 1.562, I'm going to go grab that number and add negative 7 to it. So subtract negative 5.437. So negative 5.437i, and this would be minus 3.863j. 8.63j if I add 5 to a negative 8.8. So it's in quadrant 3, which is what I expected. If I plot those coordinates, negative 5.4, 2, 3, 4, 5.4 is here. So basically I'm kind of going out to here. And if I go down, I'm not going to draw that. Negative 5.4, I'm just going to plot the 1 point. Negative 5.4, negative 3.8 is about right here, which means my vector sum, a plus b, is right there. Now I want to show you something interesting about a plus b in relationship to the other two vectors. If I were to copy vector b, and so I have two copies of it, and move vector b right here, notice that I can go from A to B by going tip to tail. So the tip of A is connected to the tail of B, and my sum goes from the beginning of A to the end of B. I can also do the same thing with A. Move A down here, and I could say take the tip of B connected to the tail of A and then move it up, and I would find vector A plus B going from the tip or the tail of B to the tip of A. Also notice that A and A are parallel to each other. B and B are parallel to each other. They're the B and B are the same length. A and A are the same length. So I've just created a parallelogram, and the sum of the vectors is the vector that goes as a diagonal of this parallelogram, and the direction of the vector goes from the origin, just like these two did when they are tip to or tail to tail. So the vector sum, vectors have to be added tip to tail first of all. So if I'm adding one vector to another vector, I have to position them like this, and the result, the sum, A plus B, will go from the tip of one to the tail of one to the tip of the other. Secondly, if I have two vectors and I create a parallelogram with them, like so, if I start at the point where their tails are together, the sum of the two vectors is just the diagonal of the parallelogram. Now, I can also go back now just for a little additional practice and say, what is the magnitude and direction of vector A plus B? So I know its components. Here it's two components. I can find its magnitude and direction now. So I know that the magnitude of the sum, vector A plus B, is the square root of the two components squared, the sum of its two components squared, negative 5.437 squared plus negative 3.863 squared, and its direction is inverse tangent of negative 3.863 divided by negative 5.437. And since that's going to be notice that's going to be inverse tangent of a positive number, which is going to be a quadrant 1 angle, but I want a quadrant 3 angle, so I'm going to have to add 180 to that. So let's do that on the calculator, and we'll get those answers. And then we'll move on to our third vector video that has another example of using some application problems. So I wanted to do the square root of, and I'm going to just go grab this number here. Oh, where's my components here? Actually, I don't have them both here. This is one of them. So let me go back up. Only I want to square that number, and so you know what I'm going to do? I'm going to remove the negative sign so that when I square it, I'll get the right answer, or you could put it in parentheses, either way. And then plus, what was the other number I had? 3.863. So 3.863. Now, does it bother you that I'm not putting negative signs? It shouldn't bother you, because when you square a negative number or you square a positive number, it's still going to be a positive number. So 6.669 is the magnitude, and now I use inverse tangent. Oh, I guess I've got to get it from here. Inverse tangent of except I want y. I want the 3.863 first. Negative 3.863 divided by negative 5.437. If I had all these on my calculator, I'd be just subtracting them. That gives me 35.39. I need to add, I forgot to add 180 to that. We'll add 180. And there's 215 degrees and 215.4 degrees approximately. So this was like 6.67, 215 point, there's the bell, 215.4 degrees. Let's see if that looks reasonable. Looking back up at our vector, that looks very reasonable for 215 degrees. Since this is, it's Mrs. Tolles. This is 9 and this is 8.8, so that looks reasonable that that's about 6.7. So next video, some examples.